So today we want to talk about inequalities and absolute values. Yesterday should have been a quick review of just basic algebra review, simplifying exponents, solving basic equations. So today we were going to expand that a little bit. We're going to talk about inequalities and absolute values. Absolute values can get kind of tricky for students. It's actually one of the, I don't want to say one of the more difficult, but it is a little bit more difficult than some of the things that we'll get into in the coming weeks. The way pre-calc is scheduled here, we'll start off with some of these harder functions and some of these harder concepts, but then once we gear back a little bit into specific examples of functions, we'll start off with basic linear functions, basic quadratics. And once we do that, usually it feels like stepping back a little bit for most students, because most of you guys are pretty familiar with, in your high school education, linear functions, straight lines, and quadratic functions. I think they hopefully beat that to death in high school. It'll be a little bit quicker in college, but as well, we might have some added things in here with these inequalities. So what is an inequality? So we want to start off with interval and set notation. Some of this stuff might be a little bit new to you guys, and particularly set notation. So interval notation, hopefully you guys have seen, but we'll write things like 2, 5. And if the video ever gets a little blurry, or if I'm like off the page, so if I'm like writing down here at the bottom and you guys can't see, just chime in. Someone speak up and let me know. I'll try my best to kind of watch my video as I'm writing and as I'm lecturing, but sometimes I'll get a little distracted with what I'm doing over here. So if you guys ever can't see anything, just let me know. So you guys have probably seen stuff like this, 2, 5 with a square bracket, or sometimes we use round brackets. The other way we write this is with set notation. So set notation, think of a set as just a collection of numbers, usually on the real number line. And we always write sets with squiggly brackets. And we'll write things like this. So the squiggly bracket says the thing we're describing within the squiggly brackets is a set. This part here, we just mean, so essentially we can read it as the set of x's, or the set of variables. This sideways e just means in. So x in r, this is a real number. Numbers. And then the vertical line here, it's kind of a logic line. We just read it as such that. I'll abbreviate such that. It's kind of a math phrase that comes up quite a bit, ST. And then we have our bounds. So it's the set of all x in R, the set of all real numbers such that the real number is greater than 2 and less than 5. We often like to draw number lines to describe these. So visually, we would graph this just by plotting 2 somewhere on the number line, 5, and then we want x between 2 and 5. And remember that the equal sign we always draw with a closed dot. Without the equal sign on the inequality, we just leave an open circle. And then we would shade in between there, since we want x's in between. So likewise, we have intervals with potential infinities. So things like minus infinity to 3. Whether it's infinity or minus infinity, we always use open brackets. Other big thing is that we always put the numbers in order. So it's the lowest number, comma, highest number. So negative infinity, comma, 3. we can write this in set notation as the set of all x in the real numbers such that x is less than 3. And our number line is just everything less than 3.
What's that symbol that symbolizes n? Can you draw it like a little bigger just so we can see what it looks like?
Yeah, so it's literally like just a C with like a line here. It's kind of like a script E type thing.
Thanks.
Yep. Another way, so you can think of it as it also means element. So x is an element of the real numbers is another way you can read that. Of course, greater than, if we're going off to positive infinity, we'll have x and r such that we can write it as 4 is less than x, or if you want to change the direction of the inequality, you can have x greater than 4. So all of those are the same thing.
Can you move the page up for a second?
Anyone still writing? Our last one, if we write minus infinity to infinity as a set, this is just all real numbers. So sometimes we'll just write that as this. This is called a blackboard bold. It's like an R. We just draw an extra line since you can't really draw bold scripts with your pencils. And of course, it's just the whole real line.
Where it shows x is greater than, what is that after?
X is greater than 4.
Okay.
The other things we'll see are intersections and unions. Intersections are denoted by an upside down U. Unions are denoted by just a regular U. Intersections also have a logic implication. They mean and statements, which means both things have to be required, whereas unions logically mean or statements. We can have one or the other. Doesn't matter. And so if I write things like 2 to 5 intersect with minus 3 to 4, and you also want to think of as the overlap, only the overlap. So for example, if we were to plot this, I'm not going to draw it to scale since some of the numbers might be off. So minus 3, then we've got 2, 4, and 5. So let's draw 2 of these guys. So 2 to 5 was this part. Minus 3 to 4 is going to be that part there. Intersection means we kind of want to just smash these together and see where they overlap. So it's only going to be on those 2 intervals. So the intersection Let's write it out. So 2 to 5 and 3 to 4. What are we going to get?
2 to 4.
2 to 4 inclusive. We will include both of those endpoints too. 2 to 4. Whereas or means union, and by union, you can kind of think of just gluing them together. Yeah. So if I change the operator there to a union, we've still got the same pictures, 2 to 5 and 3 to 4. But now, instead of just looking for the overlap, when I smash these two things together, we want everything. And so what do we get? Minus 3 to 5, but we're not going to include the endpoints here.
So the answer for these is expressed with the number line.
So this one we can simplify. So this is the number line is just an example of how to illustrate it. The way you would want to write the answer. In this case, there's nothing to be done. Actually, I guess we should write it. So in this case, we would want to essentially write what is left. So in this case, since we had 2 to 4, we want to write it as 2 to 4, and since we're including the endpoints, square brackets. Likewise here, we'll have it as minus 3 to 5, open brackets. So sometimes you can't simplify them though, in particular with the unions. If the set are disjoint sets, so for example, if we have something like minus 1 to 0 union 2 to infinity, and let's include 1 for the sake of including 1. This can't be simplified in any sort of simpler set notation because they're disjoint. This is going to be the set represented by this guy. So minus 1 to 0, and then 2 to infinity. So we shade in minus 1 to 0, including 0 but not 1, and then 2 to infinity. Like that. And so we can't reduce it in terms of a simpler set description. Any questions on those guys? All right, so we've got inequalities. And the best way to solve inequalities is just to kind of jump into examples. So if we have something like 3x minus 2 is greater than x plus 8, inequalities, all of the normal problem solving techniques are still going to apply. The only thing we do have to be mindful of is whenever we multiply or divide by a negative number. So our first step is going to be add and subtract, put all the x's on one side, add and subtract, put all the constants on one side. So I'm going to subtract the x over, and then I'm going to add the 2 over. And now we divide both sides, and since we're dividing by a positive 2, we just get x is greater than 5. So our solution, most of the solutions you're going to want to write in either interval or set notation. And since it's a greater than, we want a round bracket, 5 to infinity. When we do have a negative sign, so for example, if we have minus 2x plus 3 is less than or equal to 7, same problem solving techniques. All the x's are already on one side. All we have to do to isolate our x's is subtract 3 from both sides. And now when I divide by a negative 2, remember that the inequality flips. So if it's an equal sign, there's always going to be an equals, but the less than turns into a greater than. And so our solution in this case is minus 2 to infinity.
And that's because you divided? That's why it flips?
Because we divided by a negative number.
Okay.
So multiplying or dividing by a negative number flips the inequality. And so our last layer is we want to add in these inequalities with absolute values. Think of an absolute value. When I write something like the absolute value of x equals 3, you want to think of absolute values as distance. In this case, this says we were looking for a number whose distance from 0 is 3. And so our solution here is we get x equals 3 and then x equals minus 3. If I have something like the absolute value of x minus some number, that number is then considered the base point. So for example, x minus, let's say 2 is equal to 1. What this means, this is a number, or the set of numbers, I guess we could say, whose distance from 2 is 1. And so how do we solve stuff like that? Well, what numbers are a distance 2 away from, or excuse me, a distance 1 away from 2? We can describe that by the number, or the number minus 2 could be 1. In other words, the number could be 1 above 2, or the number could be negative 1 above 2. The way we solve absolute values in general, when I isolate my absolute value and want to get rid of it, we split it into 2 separate equations. One equation is always going to be, whenever we just get rid of the absolute value sign, what's left? What does the equation look like? The other equation we obtain by getting rid of the absolute value and multiplying the expression on the right by a negative number. And now we solve each of these pieces. So we will get x is equal to, adding 2, we'll get x equals 3. Adding 2, we'll get x equals 1. So we simply only have 2 numbers. Keep in mind this is not an interval. If we wanted to write these as sets, if we wanted to write our set notation, you just write the numbers in a list. Or here, we would write the set 1 and 3. So squiggle brackets with commas as numbers, it just means those individual points. what's going to happen when we throw in absolute values? You can essentially read those inequalities as the same thing, except now we want a set of numbers whose distance from a specified number is either greater than or less than a given distance. So for example, if I have absolute value of x, and let's say plus 1 is greater than or equal to, let's say 2. So note that the sign here is a plus. We want to think of it as minus -1. So that this -1 is your base point. In other words, we can read this as the set of numbers whose distance from -1 is greater than or equal to 2. And so how do we solve it? We remove the absolute values to get our first equation. And then we remove the absolute values, but multiply by a negative sign on the opposite side, on the right side. And since we're multiplying by that negative sign, we have to flip the inequality. So one extra step. In the last example, we didn't have to flip anything because it was just an equal sign. With absolute values and inequalities together, the second equation you get, when you change the sign of the right-hand part, you have to flip the inequality. And now we want to solve both of these simultaneously. One other thing to note is that greater than or equals means or as a logical statement. And you always want to reduce the problem down to the absolute value. So we'll do a harder one as we keep going. But the first steps of doing these problems is to reduce your algebraic statements so that the absolute value is on one side of the equation and nothing else. So it's just absolute value of something. And then our next step to get rid of that, we split it into two different equations. And it's the inequality that is left, the inequality that remains when you have it reduced to this form, when it's just an absolute value on one side, that gives us the logical statement. So I'll repeat that as we get going. So we have an or, and remember, or means union. Solve both of these, we will get x is greater than or equal to 1, and x is less than or equal to -3. It was an or statement, so we simply have to union them. X is greater than 1 or equal to, you have 1 to infinity, and here we have x is less than or equal to -3. It'll be minus infinity up to -3, including -3. And since we had an or, we want to union them. And we just got to be careful. We want to write them in order, right? So these are the negative numbers. That should go on the left. Just by the way we wrote the equations and how it ended up solving, you know, the order of those doesn't matter. But when you write your final solution, you want to write it as an increasing number line. So our solutions go from minus infinity up to 3 to -3, and then union 1 to infinity is our solution.
So what was the point of that second step that you did where you changed it from x plus 1 to x minus -1?
To this guy?
Oh, the with the blue writing.
Oh, this was just to kind of illustrate where the base point was. And so let's do this graphically and to kind of illustrate what's going on here. So -1, you kind of want to think as like the center of what's going on here. And what did we find? We were looking for the set of points, just sort of in words, the set of points whose distance from -1 is greater than or equal to 2. So here's -1, and if I walk 2 steps away from -1, either above or below, where do we end up? So 2 steps above, we end up at +1. 2 steps below, we're at -3. And what was our solution? Well, my distance from this -1 had to be bigger than 2. So graphically, this is our solution set. And notice how that coincides with our interval notation. -infinity up to 3, union 1 to infinity. And then also kind of notice how that coincides with our words, right? If we look at these points here, the distance from any point over here to this -1 base point is more than 2 steps away. Does that make more sense?
Yeah.
Good.
So that step wasn't actually completely necessary. You were just showing us.
No. So I was just trying to illustrate kind of mathematically what's going on. This step is not necessary if you're kind of just thinking of a stepwise process for how to do these. We'll do that with the next one. So all you want to do is isolate your square root first and then go through these processes. So let's do one more hard one, or at least more involved problem. Let's see. So let's do -3 times the absolute value of x minus 5. Let's say +7 is greater than or equal to -11. So let's write down our steps. If we're just given something like this, our goal is to isolate absolute value term. At least our first sort of primary checkpoint for solving these problems is isolate the absolute value term. So here we're going to add and subtract any constants. So we'll subtract 7 first. And then we're going to divide by 3, -3. When we subtract 7, we'll get -3 times the absolute value of x minus 5 is greater than or equal to -18. When we divide by the -3, we will get x minus 5. We're dividing by negative, so we switch the sign, and we will get x minus 5 is less than or equal to 6. Once we've isolated an absolute value term on one side of the inequality, we want to split into 2 equations. And of course, we want to flip the sign when we multiply the right side by a negative. And we could say -1 if we want. So we split into 2 equations. We get x minus 5 is less than or equal to 6. That one's always easy. And then x minus 5, flip the sign, and multiply by a negative. So x minus 5 greater than -6. Now, the sign here, or our inequality, was a less than. So our less than or equals to's or less thans are and just for putting it in the notes, our greater thans and greater than or equal to were our or statements. So because we had a less than here, we need an and. So we're looking for the overlap. Both of these things have to happen simultaneously. So when we solve, we will add 5. X is less than or equal to 11, and x is greater than or equal to -1. And so what is our solution? If you wanted to draw these out or draw out the picture, we have minus infinity up to 11, including 11, and means intersection. And we want x's greater than -1. And since we're taking the intersection, our solution ends up being -1 up to 11. So our last step we did, solve both inequalities. And I guess the last term would be to simplify the intervals or the solution set based on whether it's an and or an or. So in this case, we had an and. Of course, each of these inequalities that we split from our two equations gave us two separate sets. Because we needed the intersection, we could simplify that to just -1 up to 11. Any questions on that guy?